Hello everyone, welcome to this video. I would like to present our work, a robust data-driven approach for dynamics model identification in trajectory planning. In our work, we propose a data-driven modeling framework using a sphere regression technique to find the governing equation of dynamic systems. With this approach, the period knowledge of features from simple structure can be used to deduce which are complex structures. The feature library is verified with a fully autonomous machine learning algorithm composite of the L1 regularization and proportional filter. Our work proposed a method inspired by Cindy to determine the torque equation directly for complicated systems. The main contribution of this work include the development of a general scheme inspired by Cindy to obtain the torque equations from the real-world environment measurement and the robustness validations for this approach. Trajectory planning for obstacle avoidance with minimal energy based on the global interior points method and the reliability test of the approach by comparing the data-driven and closed-form solution. The visualization for the general trajectory is shown in the end of our work. Here, let's focus on the sphere modeling for estimation. The complete flow chart is shown in this page. The approach can be split into two parts: the generation of torque model and the corresponding library, and optimization of coefficient regression. In our work, a novel denoise approach is applied by estimating the noise signals as a latent variable relating the measurement and the real dynamics model. This method drives out the accurate noise signals from a small dataset as an individual signal rather than smoothing it. Now, let's talk about how to generate the dynamics model. Our approach is inspired by Cindy. The general form of Cindy can be stated as equation 1. After the noise method, the last term of the equation is eliminated, shown as equation 2, where C is an n-dimension weight coefficient corresponding to the features inside the library theta. X is the kinematic displacement of the model. In order to handle the energy optimization, the approach in our work regress torque models. The torque vectors is represented by tau can be derived by the Lagrange equations as so. The torque Cindy state as equation 3. Therefore, the main objective is to find the relationship library C. The library consists of linear and nonlinear factors. The potential library factors for complex systems usually is a deduction from a simple structure and then joined together by a further combination of simply terms. For example, the 3-degree of freedom manipulator using our work is inspired by the period knowledge of 1 degree of freedom planar and spatial 2 degree of freedom manipulator. Many norms optimization techniques can solve the coefficient C, and commonly regularization approach include ridge, lasso L1 regularization, and the least square Bayesian optimization. Our work present a new way to keep the final model sphere and close the true model. The pseudocode for software implementation is shown on the right-hand side of this page. The regression is described as equation 4. The basic idea is to eliminate the least correlate terms and update the lasso penalty coefficients in real time to sphere the library. Then regress a new library and sphere this again until the least exist terms is greater than its threshold. Then let's talk about how to get the training data for our sphere model regression of 3-degree of freedom robot manipulator. We will use the analytical method to simulate the manipulator and get angular velocity, angular acceleration, and torque. We can see Lagrange equation described by air with respect to time. Angular velocity is equivalent to the difference between total kinetic energy and total potential energy in the following equation. Because of the time derivation of Lagrange equation, the robot dynamic equations include additions and angular acceleration. These are two approaches to get the training data. One is to solve the ODE, but it can only solve the ODE for one torque value at a time. So we generate some random trajectories using quadratic polynomials to get the training data. Then We use the training data and fit the dynamics model, which will be applied to generate trajectories with minimal energy and to avoid dynamic obstacles. Let's move to dynamic obstacles avoidance with energy optimization. After getting the estimated torque equation, we will use quadratic polynomial to take place of the angle, angular velocity, and angular acceleration. The total power is the sum of the absolute values of the products of all torques multiplied by the angular velocity. To obtain the total energy, the trajectory is split to several segments, and the time is normalized to simplify the energy calculation. The penalty function is introduced to avoid the dynamic obstacle. You can see the pseudocode here. The total energy is the sum of the total power of each period of time multiplied by the product of each period of time. The alpha can help to converge the objective function. Tn is the normalized time. T is the time we want. Here is 2 seconds. T0 is the beginning time. Here is 0, and the sigma is the total time. The distance from the elbow and any factor to moving obstacle is updated in every segment. The lambda is the threshold to hold the distance to keep robot safe. The penalty function is to activate only when the distance is over the threshold. After generating a new trajectory, the boundary condition and sample volume of trajectory point are updated. Finally, the interior points method is to optimize the nonlinear model to get the parameters of the optimal trajectory. Here, you can see the results we get. In this figure, we can see the torque data at 5% noise level and the denoise data. The denoise data is quite good. Now, the figures show model selection from the best alpha parameters relating to the lasso regularization. The estimated model is regressed at the best alpha values, which is selected from the alpha selection. Then you can see the torque estimate using our torque Cindy and feature selection. The evaluate method is to use mean square error. All the torque values have low mean square error, which can show that our method is robust to noise and approximate to the ground truth. We also use some simple models including mass spring damper, double-pendulums, and spherical pendulum to verify the robustness of our algorithm. All estimate models have low mean square error, and it is also easy to compare the difference of the ground truth and the estimate model. It is quite the same. Finally, we use the identifies dynamics model to plan a minimal energy-based trajectory to a target location. In the GIF figure, the black line is the moving obstacles trajectory. The red trajectory is only with energy optimization, while the red trajectory is the energy optimized and can avoid the moving obstacle. The left figures show the comparison between the model estimation and closed-form solution. These two methods require a little more energy and when avoiding obstacles, but not much. The total energy and the maxima total powers of identified model are both a little bigger than the ground truth model, but even this is almost the same. In the right figure, it is easy to inform that the dynamic obstacle avoidance algorithm can work well. The full line is with obstacle avoidance, while the dashed line is without obstacle avoidance. In conclusion, our algorithm can identify complicated dynamics models well, and this model can also be applied to plan an energy-optimized trajectories with moving obstacle avoidance. Thank you for listening and your attention.